Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and in today's short application exercise, we'll program and test a PLC-based 2-wire motor starter. We'll examine the system's behavior in normal operation and its response to emergency stops and overloads. This lecture is predicated on the assumption the viewer has watched the Commissioning a PLC System featuring the TECO SG2 PLR lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please take the time to do so now. This aforementioned lecture configured a TECO SG2 PLR, an inexpensive basic PLC, to direct the operation of light industrial 120 volts line to neutral, 208 volts line to line, 60 Hz 3-phase AC primary circuit, configured such that the F contactor energizes a squirrel cage induction motor in the forward direction, and the R contactor energizes a squirrel cage induction motor in the reverse direction. The F and R contactors are mechanically interlocked such that they cannot be simultaneously closed. The PLC has been configured with the following field input and output devices: a normally open maintain contact selector switch on input 1, a normally closed momentary contact red push button on input 2, a normally open momentary contact green push button on input 3, a normally open momentary contact yellow push button on input 4, the normally open auxiliary F1 contact of the F contactor on input 5, and the normally open R1 auxiliary contact of the R contactor on input 6. The first 4 field input devices are intended for human-initiated interaction with our system, whereas the auxiliary contacts on inputs 5 and 6 serve as feedback about the status of a particular contactor. Note the maintain contact normally closed estop is not a direct input to the PLC, but rather serves as a hardwired bottleneck through which all 6 field input devices immediately downstream of it must negotiate to issue input to the PLC. Wired in this fashion, the hardwired estop effectively severs all incoming communication with the outside world without the necessity of resorting to any programmed instructions to do so. Let's now examine the field output devices. Electromechanical relay output Q1 directs the operation of the F contactor coil, hardwired with a normally closed overload contact. Electromechanical relay output Q2 directs the operation of the R contactor coil, also hardwired with the same normally closed overload contact. This hardwired connection between the 2 contactor coils and the normally closed set of overload contacts allows the overload to have the last say as to whether the motor is energized or not, and never surrenders complete authority to the PLC. Wired in this fashion, the normally closed overload serves as a means of directly de-energizing either contactor coil in the event of an overload without the necessity of resorting to any programmed instructions to do so. Electromechanical relay output Q3 directs the operation of a red pilot lamp, and electromechanical relay output Q4 directs the operation of a green pilot lamp. Again, note the maintain contact normally closed estop serves as a hardwired bottleneck through which all field output devices immediately downstream of it must negotiate to be energized. Wired in this fashion, the hardwired estop directly above stream of all field output devices effectively severs all outgoing communication from the PLC without the necessity of resorting to any programmed instructions to do so. For the purposes of this exercise, we will not be making use of all field input and output devices. However, this base system is configured as such for other exercises that may need this additional functionality. Given this PLC can be quickly programmed and reprogrammed as we see fit without the time-consuming necessity of physically rewiring it, this and the next several labs making use of this system should be relatively quick and painless. Here's the pared down schematic representing only those field input and output devices and primary elements we'll be making use of today. As you will no doubt recall, a 2-wire control circuit as implemented using traditional hardwire relay-based ladder logic is one that does not maintain or remember the last asserted state because it does not feature a holding circuit. 2-wire control circuits commonly make use of automatic inputs like pressure, float, temperature, or limit switches and are employed in applications where the unexpected startup of the system does not have the possibility of injuring an operator. If you necessitate review of 2- and 3-wire control circuits as implemented using traditional hardwire relay-based ladder logic, you are encouraged to revisit the 2- and 3-wire control circuits lecture available at the Big Bad Tech channel. For the purposes of this exercise, we're going to use the normally open maintain contact selector switch on input 1 as our simulated automatic input. This simulated automatic input could be some normally open pressure, temperature, float, or limit switch that, when triggered, initiates operation of the motor in the forward direction. Long story short, when the simulated automatic field input device on input 1 closes, the F contactor coil will be energized, the F contactor would close, and the motor would turn on. When the simulated automatic field input device on input 1 opens, The F contactor coil is de-energized, the F contactor opens, and the motor turns off. A simple PLC-based 2-wire control circuit can be implemented in the following manner. Note rung 1 contains a make instruction examining input I1 in series with output Q1. You'll note neither the estop nor the normally closed overload make an appearance in the program. However, these devices are readily apparent in the hardwired schematic. Wired in this fashion, the estop and normally closed overload serve to override the PLC program in the event of an emergency stop or overload event, though this protection is not without its limits, as we'll demonstrate shortly. Rung 1 alone could demonstrate the behavior of a PLC-based 2-wire control circuit. However, since we've got a bunch of input and output devices at our disposal, given this pre-configured system, we may as well put some of them to use.